Before we end this section, we're going to take a look at one more derivative rule that's going to be really useful for us moving forward. This is going to require a little bit of an exploration. We're going to be interested in seeing what it would be like to try to compute the derivative of an exponential function. That is, a function that looks like b to the power of x, where b is some positive real number constant. So notice this is almost kind of like a reverse in some way, or a flipping of some way of what the power rule was dealing with. Power rule was dealing with x to a number, and now we have number to a power of x. So what exactly are we going to do here? Because the power rule doesn't apply. Well, again, if I ever want to take the derivative of a new type of a function, I got to go back to the definition. So I will go ahead and start here by stating that we will use the definition of the derivative to compute. Let's see. I'm going to see that f prime of x would be given by setting up a limit as h goes to 0. And I would have here f of x plus h minus f of x over h. Now let's see what this looks like. If I was to go to the function of f and replace all x's with x plus h's, I would get b to the power of x plus h. And then I would subtract from that b to the power of x. That's the original function itself. Now, what the heck am I supposed to do with this? Because this looks unbelievably messy. What I'm actually going to do to work with this is I'm going to think carefully here about properties of exponents that I can make use of. And one such property would be that if I ever have something, remember like an x times an x squared, I know that I can rewrite that as x to the power of 1 plus 2, or x to the third. I can kind of add those powers together. And so in the same way, if I take this in the reverse direction, I can take a base that has two powers being added and separate it out into two separate things. And so I'm going to go ahead and make use of this with my b to the x plus h. And I'll rewrite that as b to the x times b to the h. Now once I have this, you might notice that in my numerator, I actually have a b to the x in common between the different terms. Now if I pull my b to the x out, I can see that I would get b to the x, and then in my limit, I'd be left with b to the h minus 1 over h. Now in this limit, since h is what's headed to 0, not x, x can be kind of regarded as like a constant. It's going to be a fixed value that we'll decide later on. And so because of that, it is a constant that can be pulled outside of the limit. And so I'll go ahead and rewrite this one final time as b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Now this is actually a really difficult limit to compute, and it's actually rather unfortunate because we can't really finish this derivative unless we are able to finish this limit. Now if we use the calculator, we might be able to explore what this limit value might be for different numbers in place of b. I'm actually going to go ahead and pull up a calculator to try to do this. So let's see what we have. I'm actually going to go to my function right now, or functions in the calculator, and I'm going to type in something like b to the h minus a 1 over an h. I'm going to use the variable of x here just because it's a bit easier, and I'll start by picking some different values to go in place of b. Why don't I start with something like the value of 2? If I had something like this, notice this kind of looks like b to the h minus 1 over h. It's just that I have to replace h with the variable x on the calculator, and I now have a value of 2 in place of b. And I'm curious, what would happen if I kept trying to compute this limit as I moved h, that is the power and the denominator, closer and closer to 0? Well, on the calculator, it's actually possible to do this by going ahead and using a table. Now, it's not super important that for you to actually do this, so I'm going to go ahead and actually just try to do this myself, I can get to a table by clicking on Second and Table, and you'll be able to see here that if I start typing in different values that are getting closer and closer and closer to the value of 0, I can see that if this is my input for x, this is going to be the output. So I can see that if I type in stuff like, I don't know, like 0.5 or 0.1 or 0.001, I can start to see that, I don't know, this value starts to get really, really close to like something like 0.693. Okay, so maybe I'll go ahead and record this down. I'll say that we see that computing the limit of b to the h minus 1 over h as h goes to 0 is difficult. Using the calculator, we see that if b is equal to 2, then the limit of 2 to the h minus 1 looks like it's going to be roughly about 0.693. Okay, what would happen though if I did something like b is a 3? I'm kind of curious, like what would this limit be for different values of b? Well, in this case, I would then have a limit as h approaches 0 of 3 to the h minus 1 over h. Let's use our calculator to see what this would generate. Well, this would require that I go back and I change my function here. And if I was to go and take a look back at my table, I can now see that as I continue to plug in values that get closer and closer and closer to 0, it looks like I'm getting a value around like 1.099, somewhere in that range. Okay, so I'll go ahead and state that this becomes 1.099-ish. So this is kind of weird. For different values of b, this limit is going to approach different things, which is why this limit is so difficult to compute and why this derivative is so complicated. But what would be really nice, wouldn't this be nice? What if the value of this limit was just 1? Right? Like, what if this limit just evaluated to be precisely 1? Right? That would be great, because then the derivative here would just be b to the x. So I'll go ahead and record this. I'll just say, it would be nice if the limit of b to the h minus 1 over h was just equal to 1. And this seems like it might happen for some value of b between 2 and 3, right? Because when I used a 2, I got something a little bit below 1, and when I used a 3, I got something a little bit bigger than 1. So it seems like, again, if this limit was equal to the number 1, that would be really, really great. It would make this limit super easy to compute. Now here's actually the question. What value of b could actually make this limit equal to 1, right? What would be the value? Well, this is actually a value that had to be hunted down when calculus was essentially being created, right? What is a value that would make this the case? And so we could try to go ahead and figure out values that might work, right? What would allow me to get things that get closer and closer and closer to having a limit of 1? And actually, you can start to see or start to create a value that looks something, like 2, maybe 0.7, right? Like somewhere in between there, like 2.71, and like you could just kind of continue to go and go and go, and actually the value that you would actually need to create is one of the most famous irrational numbers of all time. And it's such an important number that we save it. That is, we give it a name. We call it something so we will never forget it. The number e. E is the value that we could plug in such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. That is the value. And you may recall from pre-calculus or other courses that that value of e is 2.718281, right? That rough number. In fact, you could even go to the calculator again, and in place of this, you could imagine what it would be like if instead we wrote our value of 2.718281828459, right? Like we used this value and then went back to the table. Notice that the value that I start to narrow in on is the value 1. Notice it's not perfectly 1, it's a little bit bigger still, but I haven't reached 0 yet, but that's what I'm moving towards. So this actually gives us a really, really powerful result. If e is the number that I would replace b with to make this limit equal to 1, then that tells me something. That tells me that if I wanted to take the derivative of e to the power of x, so that is b's replaced with the letter e. If I want the derivative of e to the x, I would set up all of this, and then I would get e to the x times the limit with e to the h minus 1 over h. But this limit is equal to 1, which means the derivative of e to the x would actually just be e to the x. This right here is one of the most awesome derivative rules in all of Calc 1. The derivative of the function e to the x, the formula that tells you the slopes of tangent lines on this graph, is actually the function of the graph itself. This is actually also then one of the easiest derivative rules to keep in mind. Now the derivation here is a little bit complex, and so if you have questions about it, by all means please let me know, but hopefully the rule itself is one that's unbelievably easy and that we can kind of add to this list of rules that we're generating here in section 3.3.1.